In this unit, we're going to look at exponential functions. In this lesson, we're going to look at the characteristics of the exponential function.
All right. Hi, everybody. So in this lesson here, we're going to take a look at the characteristics of exponential functions, okay, just like it says right there. So like it says, an exponential function is a function whose equation can be written in the form y equals ab to the x. Okay, we can do a little bit more of that equation than that, but that's a good starting point. And b is going to be greater than 0. Okay, and we're going to add one more stipulation that b can't be equal to 1. This right here is just to keep it from getting really boring, kind of killing it. If the base is just going to be 1, then the function will always just equal 1. There's not a lot going on there. That's kind of boring here. We make it so that b has to be greater than 0, because if we don't, then we end up with the possibility of taking the square root of a negative number, getting the fourth root of a negative number, but creating these imaginary results. We don't want that. We want to have real number solutions here. So that's why we make those restrictions right there. So now, what happens here is if we know that b's got to be positive, well, if b is greater than 1, like it says right here, then what happens here is we get an increasing function, okay? And you see that on the right here, okay? From left to right here, when we go from quadrant 2 to quadrant 1, okay, and I don't know why I changed my style of number there. From quadrant 2 to quadrant 1 here, notice that our function goes up. It's an increasing function. However, if the b value is between 0 and 1, still positive, but between 0 and 1, okay, so we've got some sort of small fractional or decimal base there, then we get a decreasing function. And again, we're still going from quadrant 2 to 1, but this time we're dropping down. We're getting closer and closer to the x-axis here. Whereas up here, we're getting further and further away from the x-axis. Now, because of the fact that we're dealing with this exponential function here, notice that, okay, so just a little note here, that if x is equal to 0, then we get y is equal to a multiplied by b to the 0. Now, when we just looked at this not too long ago in a previous video here, that when you've got b to the 0 or any power to the 0 other than 0, that's going to be equal to 1. So this is going to be a multiplied by 1, or just a. And remember that when x is equal to 0, that right there is our y-intercept, and that's what's going on over here. Our y-intercept becomes the point 0, comma a. Now let's take a look at some other characteristics of the exponential functions here. So in general, like it says, if you've got ab to the x, your y-intercept is going to be 0, comma a, okay? There will be no x-intercept, okay? As we go, depending on what we've got here, if you've got like an increasing function or a decreasing function here, whoops, and I only wanted a little sketch here, but even then my sketch did that wrong. Okay, what happens here is, for this one right here, as you go to the left, it just gets closer and closer and closer to the x-axis, but it never actually gets there. For this one right here, as we go to the right, we get closer and closer and closer to the x-axis, but we never actually get there. The domain is going to be all reals, but the range is always going to be greater than 0. It'll approach the x-axis. It'll get, no matter what number you can think of that's not 0, but that's a little bit above 0, we'll get there, but we'll never actually get to 0 here. The end behavior of the graph, we're always going to be moving from quadrant 2 to quadrant 1. And then we saw that in both those examples. The issue is whether we're increasing or decreasing. And if b is greater than 1, then we're increasing. And if b is between 0 and 1, we're going to be decreasing. Okay? So those are the characteristics of the exponential function that we want you to be aware of. And so now we're going to take a look through some questions and just let you know, like, what sorts of things are we going to ask to help you go over and illustrate that you know what's going on with an exponential function. So let's take a look at some questions. All right. Well, our first question here says, decide whether each of the following is an exponential function or not here. Okay. Let's just take a quick look here. Y equals x cubed. Okay, this is not exponential. Okay, and the reason is because the variable is in the base of the power. Okay, we typically label equations based on where the independent variable is, the x. Okay, so if the variable is in the exponent, so if the x is up in the exponent, then it's exponential. But if it's not in the exponent, it's not exponential. So this one right here, this one is exponential. Okay. This one right here, again, this is not exponential for the exact same reason that the first one wasn't. There is a power here, x to the 1/2, but the variable part of that is in the base of the power. So not exponential. Over here, so we've got a coefficient here. Well, that's not a problem. That's like our a here. But notice we've got 0.75, and the x is up in the exponent. This one is. This one is exponential. That one's good to go here. Good. Let's take a look at the next one here. Which graph represents a decreasing exponential function with a y-intercept of 0, 2? Okay, well, first of all, decreasing exponential function simply means that the value drops or gets closer to the x-axis as the x value increases here. Well, I hope you can see here that A and B are both going up, right? As you go to the right here, those are both going up. So it can't be A, it can't be B. But C and D are both decreasing. Okay, they're both approaching the x-axis, so that's good. So now I just got to figure out which one of these things has a y-intercept of 0, 2. So here's 0, 2. That looks like the solution because over here, 0, 2, the point 0, 2 is not even on the graph here. So it's got to be C. Okay, complete the table. So I tell you what, let's run straight across here with each of these things. So remember that the expression that we're looking at, the function in general, is AB to the x. That's what we're looking for here. So find the value of A. So in this first one right here, I've got 5 to the x. Well, that is taking care of the B to the x part of this. So what's the number multiplied out in front of the power? In this case, if you don't see it, we assume that it's just 1. For the second one here, 3 times 1/2 to the x here. Well, the 1/2 to the x, that's the B to the x. So the number multiplied out front, the coefficient is going to be 3. In this case right here, and I think once you understand what that A is, this gets easier to do here. In this case, it's going to be the 2 is the coefficient of the power. And over here, it'll be 4 is the coefficient of the power. For this next one here, the y-intercept. Now, remember that with that power, okay, when the exponent is equal to 0, that power goes to 1. Because x is in the exponent, when I'm looking for the y-intercept, I'm going to make x equal to 0. So that's like making that 0, 0, 0, 0. In every one of these cases here, that power goes to 1. Okay, so in the first case here, 5 is just going to be 1. So my y-intercept is going to be 1. Here, though, the power becomes 1, and I'm left with 3 times 1. 1.5 to the x becomes 1. That's 2 times 1. 0.75 to the 0 becomes 1. And that becomes 4 times. I think I said it wrong over here. 1.5 to the 0 is 1 times 2 is going to be 2. 0.75 to the 0 is 1 multiplied by 4 is 4. So what's happening there is the y-intercept simply becomes the A value. I'm just going to clean that up so I'm looking at the right thing again here. The value of B. Well, B is the base of the power. So in this first case here, that was the 5 to the x. In this one right here, it's going to be 1/2 to the x, 1.5 to the x, and 0.75 to the x. Whether the function is increasing or decreasing depends directly on the value of B. If B is bigger than 1, it's increasing. If it's between 0 and 1, it's decreasing. So in this first case here, because 5 is bigger than 1, this is going to be increasing. Because 1/2 is between 0 and 1, this one is going to be decreasing. Don't get thrown off by the decimal in this particular question here. 1.5 is bigger than 1. So as a result, this is increasing. So I don't want you to think that if there's a decimal in the base, that it's automatically decreasing. And I can understand why somebody might come up with that rule, but the value has to be greater than 1 to be increasing. In this last one, 0.75 is between 0 and 1, and so this is going to be a decreasing function. This next one is a matching Matching graph here. So we've got y equals 5 to the x. Now I got to think about that. I know that's going to be an increasing function. So it's got to, well, it's got to be b. Okay, so this has got to be y is equal to 5 to the x. That's the only increasing one we've got there. Okay, so a goes with b here. 1/4 to the x. Okay, so it's going to be decreasing. And I've got two decreasing functions here. The question then becomes, which one is it? They both have y-intercepts of 1, which I would expect here. So the way to figure this out here is let's plug 1 in for x. Okay, if you plug 1 in for x, like 1/4 to the 1 is going to be 1/4. So the y value would be 1/4. So that's what we're going to do. We're going to look at when x is equal to 1 in both of these cases here. Notice that in A, the y-coordinate is larger than the y-coordinate is here. So basically what I got to do now is I got to pick, well, which one of these two has the larger base? And the answer is C. So this would be 2/3 to the x, whereas this one over here would be 1/4 to the x. Because the y-coordinate here when x is 1, it looks closer to 1/4, and this other one here, A, when x is equal to 1, that y-coordinate looks closer to 2/3. So that's how we would split those two up there. This next one here, classify each function as exponential growth or decay and state the y-intercept. The more comfortable you get with these kinds, with exponential functions here, the easier this question is. Okay, so I know that the y-intercept is going to be my a value, and I know that whether it's increasing or decreasing, whether it's growth or decay, depends entirely on the b value. Okay, it's growth if b is greater than 1. It's decay if b is between 0 and 1. So for this first one, the a value is 5, which means my y-intercept is 5. Because the b value, because 4 is bigger than 1, this is going to be growth. For this next one, my y-intercept is going to be my a value, which is 2. And in this case, because 1/4 is between 0 and 1, this is going to be decay. Now here, don't get thrown off. The power here is 3 to the x. The base is 3. The exponent there is x. So what's the coefficient multiplied out front? Well, I don't see it as clearly as I did in the previous two. That's okay. It's still there. The answer in this case here is going to be 1. So the y-intercept here is just 1. Because 3 is greater than 1, this is going to be growth. Here, oh, this next one here, D, they're trying to be confusing because they're putting the parentheses around the coefficient. Because notice right here, this is 2 to the x. That's definitely the power. In the previous couple of cases where the parentheses were used, they were used around the base. But we don't want you thinking that that's the way you identify the base, because in this case here, the a value is 1/2. That means my y-intercept is going to be 1/2. And because 2 is greater than 1, this is going to represent growth. Here, we're now back to kind of the old way that we did that. So our a value here is 3, which means our y-intercept is going to be 3. Because 0.4 is between 0 and 1, this is going to represent decay, exponential decay. This one right here, the a value, don't get thrown off by the fact that that's a fraction. Doesn't matter. The y-intercept is going to be 1/7. And then because 3/2 is greater than 1, and again, we don't want you making up the improper rule here. At one point when we were talking about the b, we'd said that b can't be a fraction, but the implication there was it can't be a fraction between 0 and 1. 3/2 is a fraction, but it's bigger than 1. And because its value is bigger than 1, that has got to represent growth. Okay, that's what we're getting at with that function right there. So I hope that makes sense. I hope that you get quicker and quicker at that. Okay. Now this next one here, it says the graph below that best represents y equals ab to the x, where a is positive. Okay, so that means right here, without even getting into this, this means a positive y-intercept. And if B is between 0 and 1, this means decay. It's approaching the x-axis here. Okay? So taking a look here, well, we never looked at anything that acted like A. B, though, has got a positive y-intercept, and it's a decay here. So B is my best choice right now. I'm going to just choose that here. Okay, can't be C because this is growth. So it can't be C. And D, again, we never looked at anything that behaved like that. Okay? Not that we couldn't, because as soon as A, if we allow A to be negative, then that kind of reflection does occur. But A and D, right now as we speak, have negative, if I make little marks here, have negative y-intercepts. Okay? And in this particular case here, we're being pushed into a position where no, A is positive, so that y-intercept is going to be positive. Okay, D, we're going to finish this table up here. Okay, so we're going to sketch the graph here. Well, before we do, let's get the pieces down here. So x-intercept, and we're going to run through all of these kind of at a time here. Bear in mind what we had said before here. Unless these things have been dropped down, unless they've been moved down or whatever, if you've got a function that's ab to the x, okay, and we're obeying the rules that we've already laid out here for a and b here, then there is no x-intercept. It approaches the x-axis, but it never gets there. For the first one, the value of a is 2. Second one, the value of a is 3. Again, don't let that throw you off there. That 1/2 is the base of the power. So in this case, the coefficient of that is going to be 1. And in this last case, the answer is 4 here, which means our y-intercept is going to be 2, 3, 1, and 4. So maybe on our graph here, because we're going to be sketching this in a moment here, we'll put something at 2, here's something at 3, we go down to 1, and then maybe up at 4. Those are our x-intercepts. Now I'm just coming up with sketches, so I'm just approximating here. The domain, this is easy. For an exponential function here, it's going to be all reals, all reals, all reals, all reals. The range. Well, it turns out the range is actually pretty easy too. Unless we pick up this graph and kind of move it up or down here, in every case here, the range is going to be y is greater than 0, y is greater than 0, y is greater than 0, y is greater than 0. Now, we might be approaching the 0, or we might be moving away from the 0. Okay, that can change from question to question here. So the value of b here is 5. The value of b is 1.75 here, 1/2 here, and 0.25 here. So am I increasing or decreasing? Well, now bear in mind, that depends entirely on the value of b. Okay, it depends entirely on the value of b. So this is going to be increasing because 5 is greater than 1. This one's going to be increasing because 1.75 is greater than 1. This is going to be decreasing because 1/2 is between 0 and 1. And this one will be decreasing because 0.25 is between 0 and 1. So when I sketch these, my graph is going to look something like that. Something like that. And then these two are going to decay, something like that. And then this one may be a little bit sharper here, like that. Okay, and that gives you a bit of a sense as to how these things are going to look. Okay, next question here. It says the growth of a plant during a 6-month period is modeled by the exponential function y is equal to 3 times 1.25 to the x, where y represents the height in centimeters at the end of each month, and x represents the time in months. Okay, so we are going to use our graph to determine the height of the plant to the nearest centimeter at the end of the 4th month. Okay, so what we're going to do here right now is we're going to transition over and take a look at this with the calculator here. Okay, so we're going to get the answers here in just a moment here, and I'm going to show you how to do this. So let's just talk about really quickly here what's going to happen. And you're going to see we're going to graph this thing. I'm not going to bother necessarily with the grid right now here, because I'll use the calculator in a moment. This will be a better approach to this. But we're going to use the graph to determine the height of the plant at the end of the 4th month. So that's our first question. We're going to find the y-intercept, talk about what it represents. We are going to figure out in what month the plant will double its original height. Okay, and then we're going to write an appropriate domain and range for this particular problem here. So I'm going to jump over to the calculator right now, and then we'll come right back. Okay, so let's take a look at our calculator here. So we're going to plot this. We're going to go y equals, and then we want this to be 3. We're going to put brackets here, 1.25, close brackets, to the power of x. There's our exponential function. Now, we're going to adjust our window settings here just a little bit here because we know that we're going to put this in for a 6-month period. So we'll go 0 up to 6 months. And then our scale can be 1. And then our y min and y max here, well, we're talking about the growth of a tree, so it doesn't make sense to talk about negative growth. So we'll start at 0. And you know what? I'm not 100% sure how high up this is supposed to go. So let's just take a stab at it. Let's say 10. Let's see if 10 works here. Now, if I press graph, what do we get? And there we go. We see our curve starting to curve up there. Okay, so it didn't quite get to the end of the screen at 10 here. So maybe we'll go into our window and we'll adjust that y max. I'll maybe make that equal to, let's say, 20. See what happens. Starting to curve up. And there we go. Okay, so now the first question, A, says use the calculator to determine the height of the plant to the nearest centimeter at the end of the 4th month. So to do that, we're going to press second and trace to get into our calc menu. And I want to enter in the number 4. So I'm going to use the value. I'm going to use the very first option here, number 1. And it's going to sit there and wait for me to enter in the x value. So I'll put in 4. And when I press enter, you can see exactly where it is right there. Y is equal to 7.3. So I'm going to write that down. Y is equal to 7.3. That's how high it'll be at the end of the 4th month. What's the y-intercept? Okay, well, the y-intercept, I'm going to press second trace again to get back into this menu here. The y-intercept occurs where the x value is equal to 0. So I'm going to do value again, and I'm going to plug in 0. And we get 3. Okay, now, and I could have figured that out without using the calculator to do that because I know that the y-intercept is going to be the same as the a value. So the y-intercept is going to be 3 height. We're starting with an initial height of 3 centimeters here. Now, during what month has the plant doubled its original height? Well, what that's asking me for here is it's asking me where is the y-coordinate equal to 6, double the original height here. Now, to do that, to get a y-coordinate, I actually have to go back into y equals. And I have to tell the calculator to put 6 in to a different y value here. So now when I graph this, now what I'm looking for here is that y-intercept, okay? And so you can see right here, sorry, not the y-intercept. I'm looking for that point where they intersect here. So I'm going to press second, trace, and I'm going to look for where these two lines are going to intersect here. And I'm looking for that x-coordinate. What month did this occur in? And it looks like... oh, I'm sorry, escape. That's asking me if I'm on the first curve. That's interesting. I forgot that was going to happen here. So am I on the first curve? You press enter. Did it jump to the second curve? Yes, it did. I'm going to press enter there. Calculator's asking me if you can use this as a guess. Just press enter. And we get 6. So what happened here is that we got to 6 at 3.1 months. Now, what that means, okay, what that means here is that what month did this happen in? Well, it happened in the 4th month, okay? Because what that number represents there is that 3 months have finished and we're 0.1 of the way into the next month. Well, that's the 4th month, okay? So with that in mind, we're going to move on and we're going to put the answers back in the book there, but we're going to talk about the domain here real quick. The domain is going to be pretty easy to figure out here. It's going to be from 0 to 6 because the question basically told us what the domain is. What I don't know is the range. I know that I start at 3, but I don't know where I end. So what I want to do is I want to figure out what the y-coordinate is at the end of 6 months here. So what I'm going to do is I'm going to go back into that second trace value, and I'm going to plug 6 in here to figure out, well, where does it end? and it ends at, and I'm going to round that to 11.4. Okay, and that's what we're going to use as our maximum value here. So now let's go back to the PDF document and put our answers in. And so there we go. So the answer is for A here was 7.3 centimeters. The Y-intercept was 3 centimeters, and what was that? That was, whoops, sorry, that was the initial height. During which month was the plant double its original height? Well, again, it took a little over 3 months, so it happened during the 4th month. And then we're going to write out what our domain was. Well, we were kind of given our domain. Our domain was going to be from 0, okay, out to, what was it? It was 6 months. And then our range, well, the lowest we got there was 3 centimeters. And then we noticed at the very end there that went up to 11.4 centimeters. And so there we go. Those are our values right there for our domain and range. The next question here, so we're going to use the graphs below to answer the following questions. Now, there's a little bit of kind of thinking that has to go on with these ones to answer them as best we can here, but we're not trying to make these out to be too difficult. So this first one here is an exponential growth function, clearly. We're looking at the population in size in millions, and time is going up in days here. Now, I was asking the person that came up with this question what the intention was. And so intention basically is that this is going to stop right there, and it starts right there. Same thing with this one. This one is radioactive decay. You can see it dropping here. It starts right there. It ends right there. So our domain here, the way we're supposed to interpret this is going to start, and we'll use maybe X here for our domain here. X, it's going to start at 0 times 0, and it's going to go up to 4. But when it comes to range, that one's a little bit tricky here because this is going to drop down really, really, really quite small. However, you can't start with nothing. You can't start a population of, like, let's say animals or bacteria with nothing. So although 0 is kind of going to be our low bound here, I can't be or equal to 0. But we can go up to, and we can include that, what was it? I think it's supposed to be 80 million that we're going up to right there. Same thing over here with the domain and range here. This one is going to be from 0, our domain 0 out to 5, we're going to say out to and including. Our range, this one is a little awkward, and I admit that 100% here because the graph clearly doesn't hit those numbers the way we'd like them to. So our range here is, well, okay, this point right here on the right here is a little bit above the 0, but really not quite at like 1/5 of that. So let's say it's 0.5. I'm guessing. Okay. And actually with the amount of information that we're given here, that's okay. And then on the other side there, look, it's close. It's not quite at 20. If you pull my point away, it's not quite at 20 here. So let's just say like 19.5. Okay. And again, we're guessing, but given what's going on in this question, that's okay. So for the rest of this here, in the first one, in 4 days, what's the population going to be? Well, in 4 days, that's right here. We go up and we go over, and that one's fairly easy to read because I needed to see that just to figure out what my range was, 80 million. A population of 10 million. Okay, well, 10 million is going to be roughly halfway here. Well, sorry, exactly halfway, but I'm guessing roughly halfway when I draw that point here. So when we go over, okay, that looks like it's going to be basically 2 days. And because this is a growth function right here, I know that my b value is going to be greater than 1, not less than 1. Over here, okay, with my graph here, at a radioactivity of 10, the number of weeks is, well, when I go to 10 there, I think it's pretty clear that that's going to be equal to 1 at 1 week here, right? That's where the y coordinate is equal to 10. That's at 1 week. At 2 weeks, the radioactivity is roughly 5, a little bit less. Let's maybe say 4.95. It's a little bit less. We've been rounding or kind of approximating before that, so let's stick with that. And my y-intercept here, when you take a look at it, okay, just like we were guessing up here, we were guessing that it was 19.5. Well, that's because we were looking at the y-intercept and approximating it, so we'll say 19.5. And in this case here, the value of b is going to be between 0 and 1 because this function is decaying as we go to the right.